Okay, welcome to the deep dive. So, if you're running a machine shop, or maybe you're just fascinated by how things get made, how manufacturers take a chunk of metal and turn it into something complex and useful, well, you probably know the single biggest headache with a standard three-axis VMC.
Oh, yeah, that bottleneck. Being stuck machining only, what, three sides of a part at a time?
Exactly. And that inability to get to all the surfaces in one go,
Mm-hmm.
it means stopping the machine constantly.
Right. You have to stop, unclamp the part, turn it over, or turn it sideways.
Meticulously clean everything off.
Clean it, reclamp it, hope you got the alignment right.
And then start a whole new program. It's all that manual time, and it just eats into your margin.
Jills your margins, absolutely.
And it's not just slow, is it? It's like an open invitation for mistakes.
Totally. Every single time you manually reclamp that part, you're potentially adding a tiny bit of error, a stacking tolerance error.
And if you're doing high precision work, that tiny misalignment.
It can scrap the whole piece. Costly.
Which brings us to the solution we're diving into today, the fourth axis. It really feels like a game changer here.
It is. Fundamentally, the fourth axis on a VMC, it's a rotary axis,
Yeah.
typically called the A-axis. And its whole job is just to rotate the workpiece.
So the part itself spins.
Exactly. And that lets the machine's cutting tool access multiple sides, those critical faces, all within a single clamping, one setup.
Which takes your VMC from just doing like simple flat surfaces.
Right, basic planar milling.
And moves it into this whole other realm. Now you can do continuous complex cuts, maybe helical grooves, features on multiple faces.
Without anyone having to manually intervene and reposition the part.
It feels like the difference between, I don't know, a simple kitchen knife and a really flexible multi-axis carving tool.
That's a good analogy, yeah. But here's where it gets interesting, and this is something the sources really highlight. Not all rotary capability is the same.
Okay.
Some systems, they just index, which means the axis turns the part to a new angle, locks it, and then the machine cuts like a normal three-axis machine again.
So position, lock, cut. Position, lock, cut.
Exactly. Then you have true fourth-axis motion. That's continuous rotation, synchronized with the tool moving along the other axis while it's cutting.
Ah, okay. That sounds like a big difference in capability.
Huge. And understanding that distinction is critical.
Yeah.
It really dictates what kind of parts you can actually make efficiently.
And I guess if you don't get that right up front, you could sink a lot of money into something.
Only to find out it can't do the jobs you need later on.
Yeah.
You've limited your future capability.
Okay, so that brings us perfectly to our first deep dive area.
Huh.
Really unpacking these different ways a shop can add rotary capability. It seems like there's more than one way to spin a part.
Or spin the tool, actually. That's the key distinction.
Oh, okay.
Yeah, what's fascinating is that the choice between let's say, the two main ways to get this rotation. It's a really strategic decision for a shop. It shapes what you can specialize in.
How so?
It comes down to where the rotation happens, what it does, and things like rigidity.
Right. Let's break that down for someone who's maybe weighing their options right now. What are the main choices?
Okay, so the most common approach you'll see is the fourth axis rotary table.
Right, the kind you bolt onto the machine.
Exactly. It's often an external accessory mounted right there on the VMC's main work table. And crucially, it rotates the workpiece.
The part spins?
The part spins. This is your versatile workhorse. It's great for indexing those different faces on a boxy part, drilling holes at weird angles, cutting features that wrap around, on those prismatic parts.
So for making something like a housing or a manifold block more efficiently?
Perfect for that. It's often the quickest, most cost-effective way to get that multi-sided machining efficiency boost.
Okay, so that's the rotary table. Versatile, uses the existing spindle.
Yeah.
What's the alternative then? You mentioned rotating the tool.
Right. That's the rotating spindle head. This isn't an add-on. It's integrated right into the spindle assembly itself.
Ah, built into the machine.
Built in. And here, it rotates the cutting tool, not the part. The part stays fixed on the table.
Okay, why would you want that?
Well, think about machining really complex curves, like on a mold or maybe an aerospace part, or features at tricky angles, where tilting the tool is better than moving a potentially large, heavy part.
I see. So the part stays put, which might be better for big components, and the tool angles itself.
Precisely. It's often geared towards high-precision work, where the rigidity of that rotating mechanism is paramount.
So if I go for the rotary table, the bolt-on one, for its flexibility, am I losing out on something compared to that integrated spindle head? Speed? Accuracy?
You're essentially trading a bit of that ultimate integrated rigidity for more general-purpose efficiency and lower initial cost.
How so?
The integrated spindle head, because it's built into the machine's structure, it's inherently stiffer. It often uses really high precision bearings and a more direct drive.
And that stiffness matters when?
It's absolutely critical if your main focus is, say, high-speed finishing cuts on tough materials. Think titanium, Inconel, aerospace alloys. The slightest vibration can ruin the surface finish on parts like that.
Okay, so less vibration, better finish with the integrated head.
Generally, yes.
Yeah.
The rotary table, while incredibly useful and versatile, is still an add-on. It has its own bearings, its own mounting, so its rigidity characteristics are slightly different. It's usually perfectly fine, even excellent for most jobs, especially that high-volume, multi-sided prismatic work.
Gotcha. So, decision time. If your bread and butter is making lots of, say, cube-shaped parts faster by hitting more sides.
The rotary table is probably your most profitable path forward. Quick ROI.
But if you're aiming for those really complex, high-value contracts, maybe turbine bleeds or something?
Then you might need the specialized capability and rigidity of that integrated rotating head. It's a significant strategic choice for a shop.
Yeah, really defines your niche. Okay, so regardless of which setup you choose, table or head, the big win is unlocking new shapes, new geometries, right? You're not just making blocks anymore.
Exactly. You can now machine features that wrap around a cylinder, things that were impossible or incredibly inefficient before.
Like what specifically? What kind of parts become easier?
Oh, a whole range. Think about helical gears or complex screw threads, big augers for conveyors, camshafts for engines.
Things with twisty bits.
Yeah, twisty bits.
Yeah.
Or really any part that needs features machined on multiple angled faces. The key is doing it all in that single clamping operation.
Let's talk about that efficiency win. There was that anecdote in the source material about valve bodies that really stuck out.
The valve body example, yeah. That's a classic. So this client was making these specialized valve bodies on a standard 3-axis machine.
Okay.
And to finish one part, they had to do 3 separate setups.
Wow. So unclamp, flip, realign.
Reclamp, run program 2. Unclamp, rotate, realign.
Reclamp, run program 3. Just think about the labor time involved.
Not just the labor, but think about the 3 distinct opportunities for human error to creep into that alignment.
Right, those stacking tolerances again.
Exactly. So they added a 4th-axis rotary table, and suddenly the entire machining process happened in one single clamping.
One setup, start to finish.
One setup. They figured it cut their total production time roughly in half.
Half, that's huge.
And, just as importantly, their accuracy went up because they completely eliminated those potential reclamping errors.
So faster and better quality, that's the dream, right? The whole ball game.
That really is it. And breaking down the geometric wins further, you get 2 main categories. First, like we mentioned, helical and spiral features.
This is where that true 4th-axis motion is essential.
Absolutely. You need the machine to perfectly synchronize the part's continuous rotation with the linear movement of the X, Y, or Z axis. That's how you cut perfect threads or those auger flights smoothly.
Okay, and the second category?
Just massive efficiency gains on multi-phase prismatic parts. Think about a simple box or housing. With a 4th axis, you can machine the top face, then rotate 90 degrees, machine a side, rotate again, machine the next side.
All 4 sides and the top without ever unclamping it.
Precisely. Huge time saver, super consistent.
And then there are things like cams, right? Those irregular round shapes.
Yeah, cylindrical contours, parts like pistons with complex crowns or camshaft lobes. The rotational axis is constantly adjusting the part's angle relative to the tool.
So the cutter can follow that complex shape perfectly.
It basically turns your VMC into a very precise automated sculptor.
A very precise sculptor indeed. Okay, but sculptors can be expensive. A brand new 4-axis VMC. That's a serious investment.
It definitely is. A big hurdle for many shops.
So the big question for a lot of people is, can you get this kind of capability without shelling out for a whole new machine? Can you retrofit a 4th axis onto an existing 3-axis VMC?
Thankfully, the answer is generally yes. Retrofitting is often a very practical path.
Okay, that's good news.
It lets you gain a massive capability boost for, a fraction of the cost of a totally new machine. But there's always a but.
What's the catch?
The absolute non-negotiable constraint is the machine's control system, the CNC controller.
The brain of the machine.
Exactly. It must be capable of supporting an additional access drive, both electrically and in its software.
So if you've got a really old controller,
you might be out of luck or facing a much bigger control upgrade project first. But most reasonably modern controls can handle it.
Okay. Assuming the control is compatible, what are the practical challenges? What does a shop actually have to do to install one? I imagine getting it perfectly lined up is tricky.
Oh, alignment is the most critical mechanical step. But first is just the basic mechanical installation.
Does it fit?
Yeah, pretty much. Does the rotary table physically fit on the machine's work table without hitting anything or reducing your usable travel too much?
Yeah.
You got to check the specs.
Space constraints.
Then,
Yeah.
once you bolt it down, the alignment has to be absolutely meticulous. You need to make sure the center of rotation of that new axis is perfectly parallel to, say, the machine's X or Y axis and precisely positioned.
Why is that so critical?
If that center of rotation is off by even a tiny amount, just a few thousandths of an inch, as the part rotates 360 degrees, that error gets magnified. It creates wobble. Your features won't be concentric. Things won't line up side to side.
So if the alignment's bad, the part essentially spirals slightly off-center as it turns.
Exactly, which ruins accuracy. So, meticulous alignment is key. After that, you've got the electrical integration.
Plugging it in, basically.
A bit more involved than that. It means connecting the servo motor and the feedback cable from the rotary table into a spare axis drive amplifier, usually inside the machine's main electrical cabinet. Needs to be wired correctly.
Okay, mechanical, electrical, what's next?
Software and parameter setup. This is where you tell the machine's brain about its new limb.
Right, the jargon part.
Yeah.
The CNC needs to know this new axis exists, and your programs need to be written differently now.
Precisely. You have to configure parameters within the CNC control itself, so it recognizes the axis, knows its limits, its gear ratios, all that stuff. But maybe even more important for day-to-day use is your CAM software, your computer-aided manufacturing software. It needs a specific post-processor for that machine with the fourth axis.
Okay, hold on. For someone not deep in this, what exactly is a post-processor?
Think of it like a translator or maybe a driver, like for your computer printer.
Okay.
Your CAM software generates generic tool path instructions like, move here, cut this line. The post-processor translates that generic code into the specific proprietary language, usually G code, that your particular brand and model of CNC machine understands. Every machine speaks slightly differently.
So you design the cut in CAM, but the post-processor makes sure the actual machine code is correct for your specific VMC and its new fourth axis.
Exactly. And if you don't have a properly configured four-axis post-processor for your machining control combination, you simply cannot output the correct four-axis code. Your CAM system won't know how to tell the machine to rotate and move simultaneously.
Wow. So it's not just bolting on hardware. It's a full hardware, electrical, and software integration project.
It really is. But done correctly, it's still usually significantly cheaper than buying a whole new machine. It lets a shop scale up its capability right now.
Yeah, it feels like the smart, incremental upgrade path for preserving capital.
Definitely the smart move for many growing shops.
Which leads us nicely into the final big strategic question. Once you decide you need to move beyond just 3 axes, there's another fork in the road. Do you stop at 4 axes, or do you make that huge leap to 5 axes?
The 4 versus 5 debate.
Yeah, and the jump seems massive, right? In terms of capability, sure, but also cost and complexity.
Oh, astronomical difference in cost and complexity. This is a fundamental decision. It really dictates the entire future scope and complexity of your business.
How so? Could jumping to 5 too soon be a mistake?
Absolutely. Investing in 5-axis capability that you don't consistently need, the complexity, the programming challenges, the cost of the machine itself, the skilled labor required, you can actually sink a growing shop if the work isn't there to support it.
Okay, so let's get practical. Lay out the decision rules. When is sticking with 4 axes the right call?
Unequivocally, you choose a 4-axis VMC when your main goal is reducing setups on those prismatic, boxy parts, or maybe machining features around a single axis of rotation.
Like the valve bodies, housings, shafts with grooves or keyways, basic gears.
Exactly. If the rotation you need is primarily around one axis to present different faces or cut helical features, 4-axis is usually sufficient. And importantly, the programming is a logical step up from 3-axis. It's manageable.
Okay. So when do you need to bite the bullet and go for the full 5-axis setup?
You really need to move to a 5-axis VMC when you have to machine truly complex, organic, freeform surfaces. Things that require the tool to tilt and rotate simultaneously relative to the workpiece.
Give me some examples.
Think about turbo machinery components like impellers or blisks, complex mold cavities, medical implants like artificial joints, maybe some advanced aerospace structural parts.
Parts where the surface curves in multiple directions at once.
Precisely. And on those parts, you often need the 5th axis, which is usually a tilting axis, either tilting the tool or tilting the part, just to reach certain areas without the tool holder crashing into the workpiece. or to use shorter, more rigid cutting tools by keeping the tool angled optimally to the surface.
So the fourth axis rotates the part around one line. The fifth axis adds that extra tilt, that second rotation, to get the tool into tricky spots or keep it perfectly angled.
That's the core difference, yeah.
Yeah.
And that the fifth axis adds just exponential complexity.
In what way?
Well, the machine investment is much, much higher. But the programming, 5-axis simultaneous programming, is significantly more difficult. It requires highly specialized CAM software and operators with very specific, hard-to-find skills. Collision avoidance becomes a huge issue.
Right. Lots more things can go wrong.
Any more variables.
Yeah.
So, bottom line, for the vast majority of general machine shops, job shops looking to grow, the fourth axis is the smarter, more profitable first step.
Why?
Because it directly solves their biggest, most immediate problem, getting rid of those multiple manual setups and the errors they cause. It delivers a huge efficiency boost on a wide range of common parts.
It sounds like the fourth axis gives you maybe, 80% of the potential setup reduction benefits.
For maybe 20% of the cost and complexity risk of jumping straight into full 5-axis?
That feels like a pretty accurate way to look at it strategically.
I think so, yeah. Ultimately, adding that fourth axis capability, whether through retrofit or a new machine, it's just a foundational power-up for a VMC.
Yeah.
It dramatically expands the range of parts you can realistically quote on. It delivers huge efficiency gains by cutting out that manual handling.
Yeah.
And it boosts your part accuracy by eliminating those clamping errors.
So it's the practical, profitable next step for growth, for taking on more complex, higher value work.
Exactly. It positions a shop to be more competitive.
Thinking about that synchronicity we discussed earlier, how a true fourth axis can synchronize the rotation with the linear axis to cut things like perfect screw threads or augers in one smooth operation, makes you wonder, how does that ability, the ability to create perfectly synchronized, complex helical geometry almost automatically in a single setup, how does that capability start to change the way engineers even design parts? When they know these complex, repeatable wound shapes are now much easier and cheaper to manufacture accurately, what new possibilities does that open up for the next generation of mechanical design?
That's a great point. Manufacturing capability often drives design innovation, doesn't it? When designers know something is possible and economical, they start incorporating it.
Yeah. Makes you think about what complex shapes might become commonplace next. Anyway, that's a thought to ponder.
Indeed. Food for thought.
All right, that's all the time we have for this deep dive. Thanks for joining us.
My pleasure.
We'll catch you next time.